equilibrium, or we could be, but basically what we're trying to do is replace the loading system on the beam with an equivalent resultant force and a couple moment. And the couple moment that we're going to do is about 0.0. Just a second, guys. Frankie would black. Okay, that was entertaining. Alright, so we've got a beam, and what we're going to do is we're going to replace the forces with a resultant force, and then we're going to find the moment, the couple moment, using that about 0.0 or 0.0. So the first thing that I would do is I'm going to get the components of the force. So this component right there is going to be 450 sine of my 30 degrees, which is going to equal 225 newtons. I'm going to get the y component, which is going to be 450 cosine of 30 degrees. If I plug that into the calculator, that's going to be 389.7. This one's only in the y direction, so life is good. And then we've got this one here. So we're going to have to look at this a little differently. So the first thing I'm going to do is I'm going to do the sum of the forces in the x direction. There's only one force in the x direction, and it's going this way. And the magnitude of it is 225 newtons. The sum of the forces in the y direction, I've got 200 going up. I have 389.7 going down, which is going to give me a downward one of 189.7. Now, I didn't do that with signs, I've done it with arrows. So if you're doing it in mastering, you got to kind of figure those pieces out. Which is going to give me a resultant force of the square root of 225 squared plus 189.7 squared. And that was going to be minus. But that's okay. We've got it recorded in the right spot. It's going to give me 294 newtons. And my angle for that force is just going to be the arctangent of my 189 divided by my 225, which is going to give me a 40 degree, we'll just go ahead and write it all the way out, 40.1 degree angle, and that has it going this direction. So we have the angle in there from that direction. Everybody okay with the resultant forces on that beam, based on the forces? Good? Okay, so now if I want to do the moments, this is the moments about 0. I've got a 4, now this is one of those things you got to catch in the picture. Look where my force is here. Okay? So here's my moments. I've got the 450 in the y direction. coming down. It's my 389.7. Okay, 389.7. And it's 1.5 away. I'm going to put it as negative because this is going in this is going to have me go this direction, right? In the Y. This is for the Y component. It'll have me go that direction for the X. So now I'm going to have a that's minus, so this is going to be plus, because that's in the correct direction, 225 times my 0.2. This one has me going that way, so that's in the right direction. So it's going to be 200 times 3.5. Then this one's in the negative direction, so it's going to be, and it's already in a force, and it's 200. I don't have to worry about the distance because they've already given me the moment. If I add those together, I should get a negative 39.6 Newton meters, which I may put it into the system as 39.6 and just showing it as that direction. Making sense?
Why is the 225 times the 0.2?
Because I'm 0.2 from here in that direction, away from the center of the beam.
Okay. Oh, I see now. Okay.
Yeah, that's why I circled it, because it's not it's not usually 100. You're thinking about it on the beam. My 0.0 that I'm doing it about, I'm a gap where that force is.
Okay.
And this is problem 101, by the way, guys.
Would you be able to, like, before we have class, post the pictures that you're gonna use, so if we want to work around before we come to class, so if we have any questions? Like, it's not mandatory, but if we want to.
Well, it would be nice if I could get them ahead of time. It's more of a timing thing for me. I can try. I just know over the next 4 days, I just know I'm gonna have trouble.
Well, is there like a pattern you're following, or are you just picking?
I'm just picking them. I'm trying not to pick ones that you have for homework. Yeah, and I haven't picked the ones that I'm going to do for distributed loads yet. So that's why I said it's a timing thing. I haven't picked those yet. I might be able to by Wednesday.
Will we start distributed loads on Wednesday or Monday?
Monday we're doing the presentations on fault analysis.
That's right.
So it's gonna be on Wednesday. And I think I've got the homework all straight, right? Distributed loads homework's not due until after spring break, is that correct?
Yeah,
Because I think I got it all moved on Wednesday. And distributed loads won't be on the test next Friday. But doing something like this, being able to write the resultant force or the resultant moment is likely to be on the test on Friday. So you guys want to take a stab at it and then have me work on it? So we want to find the resultant force. And then we want to find the equivalent moment. And we want to find the equivalent moment about A, and we'll ultimately do it about B as well. And everybody got some of the forces in the X yet?
Positive? Yep.
What'd you get?
Positive 75.
Yep. And that's coming from the 650 sine of 30 degrees, and that's that direction. And this one is that direction minus the 500 cosine of 60 degrees.
Yep.
Your pen is a little bit hard to read. from me.
Yeah, I know. But I've got either a really bad marker or I've got the marker that died. How's that? Better?
yeah.
That's a little bit.
Yeah. I don't have a good marker.
I know where to go. A and B.
Somebody get a Y yet?
Negative 1295.9.
Yep. And that comes from this, a negative 650 cosine of 30, negative 300, and a negative 500 sine of 60. Everybody good with that? I got nods. This is positive. So now, the resultant force is pretty straightforward, right? It's just going to be the square root of 75 squared plus 1295.9 squared, which is going to work out to be 1298, or about 1.30 kilonewtons. Good, Kyle?
Yeah.
Okay. And then the angle is going to end up being the 1295.9 divided by the 75, and that's going to give us an angle of 86.7 degrees, and it's going to go that direction. So now if we do the moments, and this one is straightforward. I don't have, in this case, I'm not going to have the gap of the beam based on how they've drawn the problem. I'm not going to get that gap. So my moment about A is going to equal, I'm only dealing with the forces in the y direction. I'm not dealing with the forces in the x direction at all. So I'm going to get the 650 cosine of the 30 degrees, or is that right? 650 cosine, yeah, cosine 30 degrees, and that's 3 feet away. And that's going this direction here, so that's going to have it go in the positive direction. They give me my 1500, that's in the positive direction. And then this one, I've got it going that way, so it's going to have the negative.
I think we've got a question here.
Okay?
Should our 3 be negative since it's going in the,
Nope, it's 3 away.
okay,
We're accounting for the direction here.
okay.
And then it's the negative 500 sine, yeah, sine of 60, and that's 5 away. When we plug all that in, we end up with 1023. Now, Brandon, if I put the negative 3 in there, I'm going to end up in the opposite directions.
Yeah, I was just wondering, because if we was taking the moment at A, I didn't know if we would make that negative. But I see what you're saying.
Yeah, it's just, you've got to keep track of it based on how our convention is.
Yeah.
And if I'm doing it about B, if I'm doing it about B, this now becomes positive, this one becomes positive. Oops. This room, okay, is this one not, there it is. This room, we lose the lights, because I'm not in a position to, where the motion detector is in this room is a little different. So this one, and does everybody see why we don't do the 300? Why don't we do the 300?
Yeah, because it's on the point that you lose.
Yeah, D is equal to 0. It's on the point, which we use to our advantage going forward. We're going to use it to our advantage. So now all of these are going to be positive this time, so it's going to be 650 cosine 30, except now we got to do 2, 5, 5 is 10. We have our 1500, because that's how we represent things. We have our 300 at 7. And then we have our 500 sine 60 at 2. And that one's going to give me 10,1095. So we can represent this as 1.02 kilonewtons. And we can represent this as 10.1 kilonewtons. And this one is problem 102 or 103, and this is problem 102. But the forces are the same. Is this making a little more sense, guys? Okay, for you fence people, we got a fence post.
Oh, yeah, that should be okay.
And we've got cables coming off our post, and we want to find the resultant force and the moment about O. So the first thing that I do, so I'm going to get my components. So this one's going to be 300 pounds sine 30 degrees. This is 300 pounds cosine 30 degrees. This is 150. This This is 260. This one's 150. And,
Read this.
yep. And this is 150, and it's 4/5. Should be 9, right? So this is 90. And this is 120. And that's 200. So the sum in the X direction is 260 plus 200 minus 120. Oh, I know why they're different. Okay. Excuse me, 460 minus 120 gives me 340. And that's in pounds. Sum of the y's. That one has no y, so I don't have to mess with it. So I got 150 plus 90, 240. So if I'm constructing this, guys, if I'm constructing this, what's this post want to do?
Follow.
What's the post want to do if I'm constructing it?
All over.
Which direction and how? Yeah? It's going to want to pull up, so which bolt is likely to fail if I don't take into account of it? I'm going to call this one the left bolt and this one the right bolt. Which bolt is going to fail?
On what?
The left bolt. Odds are.
Looks like there's 4.
No, there's 4 on, this is a bolt here,
Okay.
and that's a bolt there. Now, if the wood fails, where are we likely to see the split? If the wood fails, we're likely to see the crack right through here, right? I mean, kind of give you a practical implication. So in order to fix that problem, so let's try to prevent the problem, what do I need to do in this system? This is A, B, C. What do I need to do in this system to make it not fail? Yeah, so what do I need to do?
You could increase the force in the negative X direction, like compensate.
Okay, I gotta increase the force in the negative X direction, alright? What else do I gotta do? I've got to make sure, and we do have a counteracting force here, by the way, because we've got these bolts in here, all right? So the best thing that I can do in order to keep this, I've got to increase the extraction. So what do I end up having to do? All right, how many of you built fence? All right. So if I put in fence, what do I got to do?
Go deeper.
I can go deeper, okay? I can go deeper. That's why we put our fence posts in the ground, so that's one thing.
Is this a corner post? Because like, if that's the case, you build a brace with another post. And
You can build a brace, but if I've got this system right there, what am I going to change? We've already got our bolts in the ground, so what can I change based on this system right there?
And put another cable in the opposite directions.
I can do one of two things, right? I can either loosen these two tensions, or I can tighten that one. Think about what you guys would do out in the field. Because I can't do anything about this, right? Can't do anything about that at all. But I gotta come along, right? That's why we put up the posts out there. We got the come along, we got our fence stretcher. So if I'm gonna do that, which one am I gonna do?
We did the 150.
I'd probably go increase the tension on the 150. If I'm going to fix the system, that's probably what I'm going to do.
How much would we have to increase it by?
Well, you want to do that? Okay. Make this a question mark. And we want to have the sum of the forces end up being equal to 0 in the x direction. Because I can't change y, right? Can't change y. Sum of the force in the x direction has to be there. And so that means that this is the question mark, right? So now I've got my 260 plus 200 minus f of x, tension in the rope. F of x is going to equal 460. And we know that f of x is 4/5. It's got to equal 460. F is equal to 5 divided by 4, 460. Punch that into the calculator. This really needs to be 575 pounds. The other thing we got to make sure of is that this bracket, that bracket right there, it's got to counteract my y-force, except now that y-force needs to be, if that needs to be 575 pounds, that's going to be 345. We know that the sum of the forces in the y direction is going to be our 150 plus 345. We know that if I do that, this system has to be able to withstand an upward force, so it's got to counteract that upward force of 495 pounds. So if I'm doing strength and materials, okay, if I'm doing strength and materials, I've got to make sure that this bracket is going to be able to correspond or be able to hold and not fail at 495 pounds. Now, what else do I have to make sure about? Since you're all doing failure analysis, what do I got to deal with?
Materials?
Do what?
The materials that you're using?
Well, I got to do materials. But we all know that if I go get a piece of wood, that's going to make, we assume that this piece of wood's not going to break at 500 pounds in that direction, okay? Because we all know about wood, right? Wood has grain to it. Which means that if my grain is along the line like this, okay, it's going to withstand forces different in this direction than it withstands forces in that direction. We know that fundamentally. Am I going to go buy a piece of wood that's going to be able to withstand 500 pounds in that direction?
So you're saying that's like, can you see me right now? So you're saying, is it like the grain's going this direction, or are you saying the grain's going this direction with the wood?
Well, it doesn't matter, okay? I'm going to go out and buy a piece of wood, depending on how I build my fence post, right? I want to make sure, and I can get that piece of wood, and it's going to tell me that it can withstand 500 pounds in the direction that I'm installing my wood. Is that the piece of wood I'm actually going to buy?
No.
Why?
Because it's gonna shear.
Well, it's going to shear, but the reason I'm not going to do it is because A, that's too close to the 500 pounds, right? What do we call that in Intro to Engineering? Anthony, what do we call it in Intro to Engineering?
We're too close to what is marginal error.
Yeah, margin of safety, yeah.
It's too close.
There's not gonna be the same that. I mean, always over engineers.
All right. Now I'm going to ask the question again. How many of you have put fence in?
I've built the privacy.
Now, you probably never put pen to paper when you've built the fence, right?
Looks good enough.
You probably not put pen to paper, but what have you guys done? So let's do a T-post. T-post has that right there, right? And we put it in so that this thing is below the ground, right? And that's also why we put in our corner post with braces. Because what's happening on our corner post? I'm going to do corner post here. we got fence going off that direction, and we got fence going off this direction, right? So I have to make sure that those fences are out there. I have to make sure I got those corner posts to help not have it pulled that way and not have it pulled that way. And that's why, how many of you guys went on the wind farm visit? They talked about the concrete underneath those wind towers. So that they don't get them to topple. Okay, I don't have enough time to do another problem, guys.
Wouldn't the centripetal force keep them pretty stable?
You're asking about the centripetal force?
Of the blades, wouldn't that keep them pretty stable?
That only accounts for the rotation around the axis up at the top. You've got blades here. That's not going to keep this stable. That's not going to keep it from toppling over.
Okay, yeah, I see. No, I don't worry about it.
All right.
I still have to